Hi, I'm Jim Nelson from Flex for the Flex Power Group, where I'm responsible as a marketing director for our AC to DC and high power DC to DC solutions, as well as battery backup units. A quick overview of today's presentation is the openEdge subgroup. If you're not familiar with it, they provide solutions for edge servers used in 5G networks. So today's presentation isn't so much on overall 5G, it's more focused on the impact of the AC to DC and DC to DC inputs to the system. So the openEdge system is powered by two redundant power supplies, one of which would be provided by minus 48 volts for traditional telco sites, as well as wide range AC inputs. And the expected split between those two is roughly 50-50, which is unique. And the additional requirement for this is you can use two AC to DC power supplies, two DC to DC power supplies, or mix and match. But the key is that whichever configuration is used, they have to have seamless performance. The agenda for this presentation is to give a quick background on 5G, take a little bit closer look at the openEdge requirements, and then finish off with just a little bit of an overview for future opportunities. In terms of 5G deployment worldwide, this is a map that was developed in 2019, so there may be some recent changes because of all of the world events. But at this time, there were 61 commercial networks set up in 34 countries. For me, that was quite impressive because I've heard of 5G for years, but just hadn't realized that it had been deployed in so many geographies already.
This diagram shows how the 5G network is set up, all the way from end users through the edge to the cloud if necessary, and for all the different paths that it would be able to take for autonomous vehicles where low latency is very critical. The path for it ideally would be from the vehicle to the edge server and then back directly to the vehicle for the lowest latency path. For other types of devices and other applications, perhaps it really does need to go to the cloud because that's where the applications are that it's ideally set for. So there would be opportunities for all the different end users to get to the right paths. So for low latency requirements, the edge would be able to take care of those. For other types of situations, then it could go back to the cloud.
So previously, we showed all the advantages of 5G over 4G. And you would think that for something to have that much of an improvement in performance, there must be a penalty to pay in terms of power consumption. So this will be just one example of how when the systems were designed, that they tried to make it on par with 4G systems. And there was some clever things that were deployed that make it to where it's even more power efficient at lighter loads. So as you can see on the table on the left, that's an average traffic distribution over a 24-hour period, and it was noted that there's a lull in the early morning hours. So in terms of having an overall power available, it's the same amount of power required to operate at the peaks during the day, but in terms of being able to take advantage of the lull overnight, as you can see in the table to the upper right, that the amount of power consumption within a system is dominated by the radio area networks. So if you take a look at what the gains were, they were able to essentially shut the system down in the early morning hours if they didn't require having full power fully available immediately during those hours. So as you can see in the table in the lower right, it did keep it full power. It's on par with the power consumption required for 4G. But if you get to lighter loads during those lulls, you can see that there were some quite significant savings overnight to be able to take advantage of the lull. So now we'll get into the details of the openEdge in terms of the power considerations. On the right shows an example of the chassis for openEdge. The two redundant power supplies are shown on the left side, and then you can see where the servers are actually plugged into the chassis as well. So to comply with the specifications, it needs to meet NEBs. There also needs to be communication to the rack management controller. This is done over PM bus, which is very common for power supplies. In addition, the power supplies have to be able to power processors. So for example, on the Intel x86 family, we use the CRPS, which is Common Redundant Power Supply form factor designed by Intel. and that gives us the ability to know for sure that we'll be able to power the x86 processor and other similar processors that have the same type of power requirements. In terms of the protection features, since these are redundant power supplies, they need to be able to share current. You need to be able to hot swap them in case you need to replace one of the power supplies. And they need to not only protect themselves, but communicate back to the rack management controller exactly what's going on. A couple of little things though, for example, and we'll get into more details later, if you look at the holdup time, meaning the amount of time the system can stay up after loss of DC or AC input, there are slight differences between the two types of power supplies, and we'll show how that can be accommodated. One other consideration for the power supplies is how does the power supply operate over temperature? So a couple key notes, there are AC to DC and DC to DC inputs of the power supplies. And not only that, there's two other versions of the products. There's reverse and forward airflow. And the way the power supply operates, whether it's in one airflow direction or the other, and also based on the input power to the power supply, there are slight differences in how much power can be delivered over temperature, and those are noted in the tables that we have. So essentially, I would say they look quite similar, but I would say for customers that have a very specific workload that needs to work at a given temperature, this will be a good first pass for the designers to see, is the power supply going to hang in there, or do we need to have a conversation with the power supply vendor to see how we can increase the performance? As was mentioned in the beginning, there's also some critical timing differences for signals that would tell the system when the power supplies have lost their input power. And these will have two different types of reactions, whether it's the DC input power supply or whether it's the AC input power supply. So there's tables in the upper left and upper right that show the individual performance for both, and a summary the chart that shows the combination of the two together. So as you can see, for the DC loss, there's quite a wide variety where the amount of time that is giving the system an opportunity to shut down gracefully could be as low as a half a millisecond to a max of 5. For the AC to DC input version of the same product, there's a minimum of 7 milliseconds that the system has to make decisions of how to shut down gracefully. This is because the power supplies have input capacitors that hold up the power supply to operate normally briefly if they lose AC to DC or DC input. But due to the physical size of input capacitors available for each, there's much more energy storage available for the higher voltage AC input, which is why the 7 milliseconds is a minimum. For the lower minus 48 volt input version, the amount of energy storage in the same size capacitor is less. So given that the products are the same size, the DC input power supplies have a shorter period of time to make those decisions. So some of the impacts that we said about timing, temperature, and those types of things, where those come into play is how it interacts with the system. So this is the block diagram of the openEdge chassis. The upper two left are the two redundant power supplies. In this case, we showed one AC on the upper left, and then the DC input version right below that. So the input connector on the DC is a very specific Anderson connector, and some people may be used to seeing lugs or different types of ways to connect the minus 48 volt input, but that's how you can distinguish between the two would be by the input connector. They both interact with the rack management controller via PM bus, and they can communicate that everything's fine, power is okay, and enable the system to be able to turn on. The output of the power supplies goes into the PDB, which is the power distribution board. That's the place where everything that's required in the sled for the processor, for example, if it needs 5 volts, 3.3 volts, 1.8, 0.8, whatever the lower voltage requirements of the sled are handled with the PDB. So the PDB takes the 12 volts from the power supplies, either passes the 12 directly to the sled for the uses that require 12 volts, or if there's a specific lower voltages required that the PDB had generated, it's able to pass those over to the sled. One additional item to note is that for the power supplies, The ones that we have shown have a little bit of detail on part numbers, but those are 2,000 watt power supplies intended for the 3U chassis. We also had a 2U chassis for openEdge, and within that, the requirements, of course, are lower than 2,000 watts. So we also have 1,200 watt version of the AC input as well as 1,200 watt version of the DC input. So taking all of those things into consideration, the key, I think, for us going forward is the power distribution board, which has lower voltage DC to DC converters. It also connects to the rack management controller. So for example, if DC to DC converters were used with PM bus interface, there could be additional information gained from the system. So if we go back to the previous slide, you can see that if the power from the 12 volts is going through the PDB, it could be saying everything's fine to the rack management controller. However, if there's something downstream where some of the lower voltage rails go into the sleds, you could have something that's actually a condition that would be normally considered a fault. But if the 12 volts looks like it's being presented well to the PDB, the system could think that everything is fine. So by having intelligent DC to DC converters directly on the PDB, there could be additional information to say that everything is just fine for the sled as well. So noting that the 12 volts is available and working correctly is great. So an additional next step for this would be, could we see if every power rail is functioning correctly? In addition, for the future, for using non-volatile DIMM memory or other things that may require much more tight coupling with the signals of power OK, and when the system is shutting off, this is something where the 0.5 to 5 milliseconds or 7 milliseconds, there could be key decisions that have to be made within that time to flush the non-volatile memory properly, and some of those requirements take more time than that. So for example, there could be battery backup solutions or other things implemented as well that effectively would extend the amount of time to be able to flush the memory and override the power OK signal being exclusively coming from the power supply. In addition to the current generation of x86 processors that are being used, there's of course obviously other people such as AMD that make processors and future roadmaps for Intel x86. So one of the keys for the system is to be very flexible and to be able to keep up with the demands of the sleds so that it truly can be backwards compatible for the future. So the key for power supply vendors is for ourselves to work very closely with the customers and make sure that we not only anticipate today's needs, but what's going to be required to really keep this backwards compatible for the long haul. So here are a couple examples to just show, for example, on the PDB, where we discussed having intelligent DC to DC converters. Here's an example where there's 3 grades of DC to DC converters that potentially could be used on the PDB, whether it's a high current requirement, medium, or low. And so these would be the types of things that have the ability to communicate to the system. If you take a look, there are a full suite of tools that are available that can work with any of the products that we had shown. And you can do things such as sequencing, which are critical for ICs, as well as just state of health and other types of telemetry from the PM bus. So this is an example of products from our power module group within Flex, and these types of products can be seen on the flex.com website. So the conclusions for today's presentations are that AC to DC and DC to DC power supplies are critical. And in particular, they're critical because they have slightly different functions that really need to be well understood and accommodated. These are the type of power supplies that can be optimized for 5G, not only for today, but going forward. And many of the features that would potentially have to change because of changing application requirements today can be done quite a bit through firmware only. These are the types of changes that can be done very quickly, can be done in the field, versus in the past where changes had to be done almost exclusively through hardware that would require replacing units, revising circuit boards, all the development time it takes to get that qualified and through a production line. So if anything can be noted way ahead of time and accommodated by firmware, it really does make a lot of potential changes for applications quite simple. And again, as we said before, the best way is to stay in really close communication. And if something starts off and changes, as long as we have as much time available to address those changes, it really makes life much easier than in the past. So in conclusion, there's some contact information for how to participate in the openEdge subgroup, including the wiki and calendar of how to participate, and would encourage everybody to do so. If there are any questions more directly related to this particular presentation, I would encourage people to address those to an email. Flexpower@flex.com actually works great. Those inquiries will get to me as well as to the rest of our team. So just want to thank everyone for participating in the online presentation. And really, it's a quite unique circumstances why we're doing this, but I really applaud OCP for handling it so gracefully. Thank you.
Hi, everyone. This is Jim. If there are any questions or comments, please feel free to ask. If there are any questions that you don't want to bring up immediately, again, if you can use the contact information in the presentation, and we'll certainly get back to you as soon as possible. So I guess one last chance if there's any questions or comments before we close. Great. Well then, thank you everyone for joining and really appreciate your time.